In this video, we'll continue our discussion with continuity. And in our first example, we're going to find where in this given function we are continuous. And so many times it's actually easier to think of it as where might you be discontinuous? And then when that question comes up, a lot of times we think about domains, right? Where are things allowed to exist? Where will things not be allowed to exist? And when we look at different types of functions, they have different restrictions. For example, things like polynomials, things like odd roots, things like sine and cosine, generally speaking, don't cause us any problems, right? Polynomials, you can plug anything in for. Odd roots, you can get anything, you plug anything in there and get something out. Sines and cosines are continuous from negative to positive infinity. So it's when we get into things like rational functions or even roots, like we have in this example, where we have to start being a little bit cautious. So the first thing that jumps out at me in a problem like this is the fact that we have a denominator, which we know it can't be zero, and we also have this even root, which I know underneath has to always be positive. So when I break that down into kind of a few smaller type of questions, it will also benefit us to know that in this particular problem, sine being bounded between 1 and negative 1 will never give us a negative number under here. Okay, it can give us a 0, right? Because if sine of x is going to be negative 1, that would zero it out. But we don't really have to worry about getting a negative number under here because we know that sine wouldn't allow it. So really, all we have to worry about in this particular problem is where 1 plus sine of x isn't allowed to be 0, right? That entire quantity can't be 0. And so the actual even root doesn't really come into play a whole lot here because of what's underneath it. Now, given other problems, you would obviously want to take those circumstances into consideration. But for this one, all we need to worry about is where 1 plus sine of x is not equal 0. So this says if I solve this, sine x equals negative 1. And of course, x equals 3 pi over 2 plus 2k pi. And remember, those are the values you're not allowed to have, right? That's where you would be discontinuous. So to answer the actual question, where are we continuous? We would be continuous for all x, such that x is not equal to 3 pi over 2 plus 2k pi. And so there would be our answer in set notation, showing where our given function is continuous. Okay, so now we're going to talk about a couple theorems when it comes to continuity of compositions. The first one says if f is continuous at c and g is continuous at f of c, then g circle f, meaning the composition of g and f, is continuous at c. Now, in my mind, that's a bit wordy. That's tough to follow. So conveniently, the book has a really nice picture of what this is saying on page 77 in your text, figure 2.42. I would encourage you guys to take a look at that. That really clarifies it, and it's a very simple idea overall. The second theorem talks about if the limit as x approaches c of f of x equals b and g is continuous at b, then the limit as x approaches c of the composition is equal to g of b. Now that one is one that I'm actually going to work an example with you and show you what the benefits are. It's actually really helpful to understand this and be able to apply it in certain circumstances. For those of you taking Calc 2, you'll get into that quite a bit when we get into exponential functions then. So let me go ahead and clear the screen. I'll get into a couple examples going, and hopefully this will all start to make sense. All right, so in this example, we always have to be careful of, again, discontinuity. So we're focusing in on t approaching 0. We want to make sure that if the things that we do deep inside the function are going to be allowed, given they exist. And so what I see in a problem like this is we have a sine and we have a cosine before I get to my tangent. Well, sine is continuous everywhere. Cosine is continuous everywhere. So that last theorem that we saw actually says that the limit can bypass the sine and the cosine and actually be moved inside the function. Now, again, that can't always be done. You have to rely upon it being continuous in the neighborhood that you're studying, in this case, t approaching 0. So for us, this says the same thing as sine of pi over 2 times cosine of the limit as t goes to 0, tangent of t. So by moving that limit inside, now all I have to focus in on is this to get started. And I know that the limit as t goes to 0 of tangent of t would of course be 0. So sine of pi over 2 cosine of 0. Cosine of 0 is 1. And so we have sine of pi over 2. Sine of pi over 2 is also 1. And so there's our answer. So being able to take a limit inside a composition is a very nice tool to have, but you got to make sure that you're continuous where you need to be. I mentioned a little while ago that the exponential function comes into play in Calc 2. Well, if you think about the exponential, it's continuous everywhere. So it would make sense that when you start working with some of these limits, the ability to take the limit inside of certain things will definitely make the problem a lot easier. All right, so the next example we look at has nothing to do with composition, so we're switching gears a little bit. This is kind of a nice summary of this idea of continuity. So we're given a piecewise function, and we're told to find the values of c so that the function will be made continuous for everything. And so to do this, we're just going to resort back to the basic definition. For this thing to be continuous, I know that the limit as x approaches 3 of f of x needs to equal f of 3. Now, I know that 3 is my point of question because of how the piecewise function is set up. That's where the break is in the graph. So I know that this definition needs to hold true for our function to be continuous. Now, let's just go ahead and take a look at it. If we look at f of 3, that means go find function f. Every place you see an x, put in a 3 and see what happens. Well, we know from the piecewise function that we need to go into this function right here. This is where 3 is a part of. We have the or equal to symbol on here, so we know we have to go into here. And by plugging a 3 in, we would get a 6 plus c. Okay, so that's the f of 3 part. Now, for the limit part, the limit as x approaches 3, that actually gives us two questions. We need the limit as x approaches 3 from the right and the limit as x approaches c from the left. Now, if we're approaching c from the right, that means we're picking numbers that are bigger than 3. The numbers bigger than 3 would come from this part of the piecewise function, right? Bigger than 3. So if I take my value of 3 and I plug it in here, that's going to give me a 2c minus 3. Now, if I come in from the left, now I'm taking numbers less than 3. I know that I'm going to have to go into this guy, which is going to give me my 6 plus c. Now, for the overall limit, this thing to exist, these two parts have to be equal, okay? So I'll take both of those parts. I'll take the 2c minus 3 and set it equal to the 6 plus c. Now, to be fair, for this thing to be continuous, all three of these things have to be the same. But because we've got a repeat here, it makes sense just to put these two things together like I have. Okay, so again, to be clear, for this thing to be continuous, all three have to be the same, but you can see two are already the same. So then when I solve this, I get c equals 9, and that is where, if I plug that in, I will make my function continuous over the entire positive to negative infinity interval. Okay, so the last thing we're going to talk about in this section is the intermediate value theorem. Now, you might have seen kind of a subcategory of the intermediate value theorem back in college algebra, but the theorem itself is what you see on the screen. Let f be continuous on a closed interval ab, and f of a less than equal y naught less than equal f of b. If that's the case, then there exists at least one c in the open interval ab, such that y naught equals f of c. Now, this notation, if you haven't seen it before, this is c is an element of the interval AB, or c belongs to the interval AB. You'll see it a lot when we deal with sets as well, but you'll hear me say c is in AB. So let me draw a picture and show you what this means. I've got some curve. Let's say that this is what we have right here. This is going to be y equals f of x. Okay? This guy here is going to be my a, and this guy here is going to be my b. Notice it starts off, f is continuous on a closed interval ab, so I went ahead and I did fill those in. Now, we've got f of a less than equal y naught less than equal f of b. Well, these are all y coordinates, okay? Now, this guy would clearly be our f of a. This guy here would clearly be our f of b. And this part says that y naught has to be between those two things. So somewhere between it, there's got to be a y naught. So I'll put this here in blue. Now, if that's the case, then there exists at least one c in AB. So that means there's at least one value c between AB such that when I plug that c value into my function, it spits out y naught. And so if I kind of move this across here and go down, there would be my c. So again, it says that if you know of a value in between two others and your function is continuous on the closed interval, then that value had to come from somewhere, right? And that value had to come from somewhere between the a and the b. Now, that's one of these really kind of broad ideas. I mentioned before that whenever you worked synthetic division back in college algebra, you might have heard of this. And so let me show you where you might have seen it there. So as an example, let's prove there's at least one solution on the interval -1 to 0 of this function right here. Okay, so we've got a basic polynomial. So we know that this thing is continuous, right? We know it's continuous because it's a polynomial. And the way I have it set up is I've got my function set equal to 0, which is essentially us finding an x-intercept, right? We're trying to figure out where if y is 0, what are the x's, which is just an x-intercept. So to do this, all I have to do is take f of -1 and f of 0. Well, f of -1 gives us -1, and f of 0 gives us a +1. And I argue that we have proven now that there is a solution on -1 to 0. And I say that because these two things have opposite signs. If we look at a picture here, and my x value here is at -1, and my x value here is at 0, -1 maps to -1, 0 maps to a +1. So those 2 points have to be connected. And not only does it have to be a function, but they have to be connected. I know that because, again, we're continuous. It's a polynomial. So I have to be able to connect these dots going from this guy to this guy. And in doing so, of course, I had to cross the x-axis. Therefore, there's got to be a solution between -1 and 0. And again, that's where at least when I teach college algebra, that's the tool that I give them to help narrow down their search when they are looking for those rational zeros. But anyway, there's the intermediate value theorem in its most general form with a small example to hopefully tie things into something you might have seen in the past.